Hello, good morning. This is Dr. from the Barcelona Supercomputing Center, and this is the second Climateurope webinar. Welcome to all those who are already connected. I suspect that there will be a few more people connecting a bit later. So we won't welcome them anymore because the session will be started already. The webinars are organized by Climateurope are consisting of two talks. Those two talks are of around 15 to 20 minutes length, and they are followed by a few questions from the attendees, plus any other questions that people might want to raise using the chat option in WebEx. So feel free to write your questions on the chat at any point of the presentation. The two presentations are followed by a final discussion around a couple of questions. The two questions are just motivation in the sense that Climateurope is a European project that aims at identifying what are the main problems and issues that will prevent researchers working on infrastructure, modeling, observations, and services in the climate context. And what we aim with these two questions that you can see now on your screen are basically collecting impressions and opinions from a network of scientists that will help us to write reports that can inform both the Commission and the community. So without any more introduction, I pass the microphone on to our first speaker, Carlos Garci from the BSc, who will be talking about climate services and infectious diseases.
Okay, thank you, Paco. A few days ago, Paco asked me to give my perspective on an aspect of climate service since I've been working in the past few years. I'm an atmospheric scientist. My expertise basically is dust modeling and aerosol modeling. And a few years ago, I was contacted by a group led by the, sorry, I cannot move this now. Okay. Led by the World Health Organization. This group is called the Meningitis Environmental Risk Information Technologies, MERIT, which was launched in 2007. And the idea was to gather public health specialists, epidemiologists, microbiologists, climate scientists to work together on the field of meningitis epidemics in the African Sahel. So what was the problem and what is the problem with meningitis? Just in a few words, here you can see in this slide what we call the meningitis belt, is where the place in the world where meningitis is epidemic. Just in a few words, we're talking here about the bacterial form of meningitis called Zeta meningitis. This bacteria is transmitted from person to person. There are typically 1 to 10% of asymptomatic carriers that grow up to 10 to 20% during the epidemics. There are different serogroups of this bacteria. Some of them are worse than others. Typically, in the belt, serogroup A has been traditionally the one with more epidemics. Excuse me, I have to move this like this. Okay. And there have been more than 1 million cases since 1998, and typically there's a 10% fatality rate during an epidemic. This is when there is treatment, and 10 to 20% of survivors suffer permanent brain damage. Sorry. Okay, now. So Here I show a little bit the epidemic waves that have happened in the last 30 years, 40 years in the belt. I show these are national data from different countries in the meningitis belt. As you see, the epidemics follow this crescendo patterns that we call epidemic waves. There are several factors that create these waves. The most accepted conceptual model for it is that there's a loss of herd immunity to certain strains of the disease, and there's the initiation of these large-scale epidemic cycles. Then, when the bacteria spreads, there's widespread carriage, there's a development of herd immunity or population immunity that limits the transition and ends the epidemic wave. These are yearly data. As you will see now, this is a dry season epidemic, and the main explanation is a combination of climate and dust conditions, in addition to respiratory infections during the dry season that decrease the mucosal protection and allow the bacteria to penetrate into the bloodstream and create the disease. So the main mechanism the main hypothesis on what is the effect of climate is by affecting the individuals that carry the bacteria and can develop disease. As you see, these are large-scale patterns. Here we have the seasonal variability of the disease. As you can see in the upper figure, you can see a seasonal cycle basically peaking in February, March. So you can see box plots here. This is I showed this to show that there's a strong interannual variability. That also here you can see in the spatial patterns we have district variability, so it's not something that is homogeneous in a country. And also if we go to finer detail, and this is Niger, here you can see that the epidemics show a very high subdistrict variability. So this becomes something very, very challenging when we're talking about climate services, because particularly health measures are taken at these scales, and typically we're working at larger scales when we're talking about climate data and modeling. What is the role of the climate and the environment? We have two main seasons, or two main patterns, climatic patterns in the region. Very basically, we have the summer when the monsoon affects the region. We have rains, there's malaria, and during the dry season, we have the effect of the harmattan, these northern winds carrying a lot of dust and low humidity. So the main hypothesis, and I'm talking about hypothesis because until very recently there were no in vivo experiments to look at the mechanisms on why this is happening. Basically, humidity is one of the factors by making the bacteria remain longer in the air and helping on the survival of the meningococci. The dust hypothesis, which there are two explanations. One, and the most accepted one, is that the dust damages the mucosa, and this facilitates the invasion of the bacteria into the bloodstream, and also the iron content of dust may be facilitating colonization because the bacteria, in fact, one of the things that is able to use to grow is iron. Then there are other effects, for example, climate enhancing viral epidemics, and these viral epidemics also helping in developing these epidemics of bacterial meningitis. There have been studies in the past. The broad spatial pattern is pretty much well explained by low absolute humidity and land cover type. The seasonality, there have been relationships with winds and dust. And there's also an effect, or there seems to be an effect in the year-to-year variability. In addition to immunity, the climatic factors have been shown to be at least partly responsible of the year-to-year variability in the epidemics. And factors that have been correlated are humidity, dust, rainfall, and wind. So what was merit and why this group was created? There was a pressing problem, which is by WHO, and which was calling for solutions. And how meningitis is managed in the belt has been traditionally done through reactive vaccination. Basically because reactive vaccines do not provide long-term coverage, only for 2 to 3 years. So the strategy was reactive, was not preventive, meaning that instead of vaccinating the whole belt, the idea was is to wait until we see if there's an indication that there will be an epidemic in a certain district, and there's another threshold and an epidemic threshold when the number of cases start to grow, and the decision is taken when the number of cases is above 10 cases per 100,000. What happens is that when this decision is taken, typically there's a need for time to deploy these vaccines, to do the action, and typically what happens is that it is too late. The epidemic cycle has already gone through, and so there was not enough lead time to make the reactive vaccination effective. So, and here is when climate services came into play. So the idea was, can we help with climate predictions or weather predictions or dust predictions to help increase the lead time to allow deployment of vaccination in time in order to avoid the epidemic cycle. There were other questions that I think are interesting from the point of view of when a scientist faces one specific problem like meningitis, and these are the questions that in the beginning were asked by WHO and by other health specialists. For example, the type of questions that were related to specific problems related to meningitis in the belt. At a large scale, one of the questions was, for example, what's going to happen in 10 to 20 years in the belt? Is there going to be an expansion of the dry conditions? Is that going to affect meningitis? So this is kind of more long-term planning, right? Of course, nowadays, the skill of decadal predictions, particularly in this region and for the dry season, is particularly low. And there may be other factors that are more relevant, for example, the circulating serogroup, or the immunity of the population to certain strains, or the appearance in the future of a virulent strain that we cannot predict, right? So in that respect, the climate scientists, we could not help responding to that question. We could give the current predictions, but current predictions are particularly tailored to the wet season and not the dry season, because models do not have a lot of skill for the dry season. At the seasonal scale, the question was, what's going to happen on the next season? It's going to be very dry, and why they were asking for these questions was not for reactive vaccination, is to estimate vaccine production. Again, this started in 2007. At that time, at least, predictability of the dry season was almost inexistent. Basically, all climate modelers were focusing on the wet season. And so this was a very, very challenging question. And as a climate scientist, we had to say, well, we are not yet there to provide confident seasonal predictions, or at least that have some value to estimate this vaccine production. So we decided to focus on the short term. And the idea was, what is going to be the risk of epidemic during the season? Are we going to be above the epidemic threshold in the next 1 to 4 weeks, when the end of the season is going to happen? So the challenges in this short-term, more shorter-term question it was at the time the availability of the observed and the observations and forecasts, particularly in these regions which are very poor, in terms of meteorology and climate, but it's more the case of dust and aerosol information. There were no networks at all, particularly of dust concentration, for example. There were some measurements of AOD by Aeronet and some satellite observations, but the interesting or the relevant parameter here would be surface dust concentration, where people breathe. Then the challenging part also was that measures are taken at the district scale. So we're talking a bit about high resolution, and this is more a challenge also for observations. We can have 1 or 2 observations, but these are only relevant locally. And then the lack of data for other factors in near real time. For example, we don't have, like the surveillance system for meningitis is not in near real time. There's data for the number of cases. But in order to think about a prediction system in near real time, we need near real time information. And of course, there's many other kind of data that we would need ideally, for example, carriage, that we cannot even dream about nowadays. So what should we do to forecast meningitis today? So the idea here is to identify whether an epidemic will occur and to predict the magnitude of incidence. That's a typical goal of an early warning system for an epidemic. However, what happens, at least in this case for meningitis, we have an incomplete understanding of the mechanisms, of the dynamics of meningitis epidemics. There's also a lack of data at the required temporal and spatial scales. All this limits the use of mathematical modeling. So like I'm talking about here about mechanistic mathematical modeling to forecast epidemics. However, in this context, in this more practical context, as you see, we're talking about thresholds here to take decisions. The magnitude of the incidence, for example, is of less interest in comparison to whether we are crossing this incidence threshold or not. So this happens to be better in terms of we don't have to be as precise, but rather analyze or see if we can predict if we're above or we're going to be above or below a threshold, right? And what we can do, and what has been done in the last few years, is to work with statistical models that are not based on climate, that are just based on previous incidents, and then climate and weather-based models. There are couple of examples. What I did personally with a larger group of people was to look at if it was possible to provide early season forecasts in Niger. Why Niger? Niger is a country with better records and historical records since the 80s at district level. So it was a very good opportunity to test this kind of framework. I would like to say that this would be like the ideal case. Data is poor, but is the best that we can have in the belt, for example. I will not go into details of the modeling, but basically we examined whether climate conditions, including dust concentration, could be used to predict meningitis incidence during January through May. Well, this is rotated here. Okay. So just important thing about the data at the time, this was 2010. 2011, 2012. There was a lack, there's still a lack of surface concentration data, right? And in order to test whether dust was a predictor for meningitis, we had to develop, in the group, a regional dust climatology from the 80s up to today. We did that with a model developed here at BSc. Basically, this highlights one of the problems. So while we had reanalysis for meteorology, in this case, one of the essential parameters was unavailable at the time, and we had to develop a new data set in that respect. More recently, there are other reanalysis data sets for aerosols by NASA and ECMWF that have come up, but at that time, As an atmospheric scientist, in the beginning, I thought I would have to just provide the modeling data, but I realized that there was not a lot of people at the intersection of what was needed in terms of knowledge. So combining this climate data with the health records, I collaborated with statisticians and medical doctors, and we created a statistical model based on climate during the early season and dust during the early season. We also used early incidence of cases. That was a kind of a proxy for carriage of the bacteria. We tested these models at the national scale and at the district level scale. We analyzed the models with respect not only with the classical skill scores, but also with respect to the specific policy question. And this is very important, I think. In this sense, for example, we analyzed sensitivity of the model and specificity. A model with high sensitivity or high specificity means two different things. For example, in our case, one limitation is that during a certain season, there's a limited vaccine stock. So that means that if there's a limited vaccine stock in a certain season, you cannot allow your system having, false positives, even if you're covering the true positives. So analyzing the skills of these models in terms of the specific policy question that you want to respond to let know the stakeholder or WHO when using a certain model like that, it is very important. So that was something that we did. We started with the national scale with early season forecast. So with information, we showed that with November, December wind and dust, and early cases were good predictors in terms of R-square. We were around 0.6, which is quite good when we're talking about an infectious disease. And in terms of sensitivity and specificity, we were also quite okay at the national level. At the national level, of course, this is an interesting information that we can provide to the country. However, as I said before, the decisions on vaccination are taken at the district scale. We analyzed the model also at a district scale. Of course, the skills of the model are decreased because there are many other local factors that we cannot take into account in our statistical models, but still, we see that we're better than just assuming that, from one year to another, we're going to have something similar. So we have a cross-validated correlation of 0.55 in terms of spatiotemporal patterns. And so somehow we showed that still with some poor information on the number of cases and with models that are not necessarily observational data, we can provide some information that could be helpful. To what extent this would be helpful in the real setting, that's another question. There were other initiatives by my colleagues at NCAR and UCAR. They showed, for example, in this study, in their case, instead of predicting the onset of the disease, they focused on predicting the end of the epidemic. This was also another important aspect because you can still have late epidemics, and they based that on relative humidity forecasts. And they showed that, in fact, by applying the methodology, of course, this was not applied in reality. This is a study that they made. By using 2-week forecasts of relative humidity and predicting the end of the season, they could have saved 2.6 million doses of vaccine that could have been used elsewhere more effectively, which means prevention of 24,000 cases of meningitis and 2,400 fatalities. So we're talking here that even with kind of rather poor settings, in rather poor settings where we don't have a lot of data, there's some information that could be vital to save lives. I'm going to end by talking about the challenges and my opinion on these issues. In the case of meningitis, there was one very frustrating aspect, and I guess that this is happening in many other fields as well. The problems change over time, and so the time scale of research and providing a service, once this is going to happen, maybe the conditions in the belt, for example, have changed. What do I mean? In 2011, 2012, there was the introduction of the conjugate vaccine. Conjugate vaccine is a preventive vaccine for serogroup A, meaning it's not a reactive approach, it's a preventive approach because this conjugate vaccine provides long-term immunity around 10 years. What happens with that? I mean, this is very good news on the side of reality. The problem for science is that we have been building statistical models in which the background conditions of the belt and the immunity of the belt was of a certain way, had a certain characteristic, and now this has changed. So this highlights the limitations of approaches that we have to follow because we don't have enough knowledge. We need statistics, and these statistics may not work because the conditions have changed. The other thing is that while this prevents serogroup A, which has been the important one during the last 30 years, the other serogroups are not covered and need to continue with reactive vaccination. But now we don't have enough data of these kind of new conditions in the belt to create statistical models that eventually work. Here I put in blue, red, and green 3 aspects: knowledge, data, and institutional alignment. And these are the 3 problems that at least we have in this case. Particularly, I'm going to highlight in this one the institutional alignment. So in terms of knowledge, we still don't understand this vaccine-induced meningococcal immunity. So even if we have a lot of good climate data, if we don't still understand this related immunity aspects, it's going to be difficult to predict the disease and to model the disease. We don't have enough laboratory research using new animal culture models, and we are still with not mechanistic mathematical models, but more statistical approaches. So this has to change in a way. In terms of data, we need a better surveillance system for meningococci, for the meningococcal disease. We don't have data on carriage, which tells us how much of the population, or at least having some information on what is the circulating serogroup, how many people are carrying it. We don't have vaccination data, and this is quite surprising, and this was something that we didn't understand when we got into. So WHO is helping in this vaccination campaigns. But there's no data, and we would need that data to know how many people have been vaccinated in the past, for example, to know about the immunity of the people. And of course, we don't have sub-district scale information, and we can see that as we go forward, we see that disease and infectious disease there's strong variability at sub-district time scales, sub-district spatial scales. For climate and that data, of course, we need improvements. We don't have enough observations in the region, particularly for dust. There's new products like new reanalysis data sets that are using observations, and there has been an improvement in that sense. And finally, the big question here. So there were several groups that we implemented some solutions. We came up with imperfect solutions, but we wanted to test that in the belt together with WHO. As you can imagine, this has to be done in coordination with the ministries of health of the countries, and not necessarily the groups of research are properly funded to do operational implementation of these aspects. There's limited funding for translational research, at least at the time in the US. So also this highlights the larger question, whether if we go into this direction, whether if the institutional alignment has to be already okay before we start even looking at it. If it would be possible to implement this kind of forecasts and that are used, so instead of just going and spending resources on analyzing this, if we have to be first implementing this infrastructure, who has the responsibility of providing these forecasts, etc. So this is something maybe for discussion, but I'm going to stop here. Thank you.
Thanks, Carlos. I wonder if there are any questions from the attendees. Martha, can you show the chat? If any of you is interested in asking a question, just unmute your microphone and we'll give you the word. Okay, well, I have a quick question while Sylvie is preparing her presentation. What are the main barriers to get access to the medical data? Because from our institutions, we are mainly involved in climate research, and we know that it's difficult to get climate data sometimes, but I have the impression that the barriers are very different in here when it comes to clinical data.
There's definitely, it's very difficult. Sorry. Yeah, it's very difficult. Definitely there's in this sense, for example, and this is pretty common to climate data, different countries that have different policies for treating their health data. In the region, specifically in this region, there's there's WHO Africa. In the case of meningitis, they gather the data from the countries, not in near real time. So we're talking about weekly data on the number of cases in a certain district. And of course, to use that data, you would have to be involved in one of these consortium where there's WHO and there's permission from the countries to use this data. Of course, this data is not available to everybody. And particularly in this case, one of the problems that we have is the quality of the data, which is very heterogeneous. It depends on the country. We also have the problem that if we really want to go to use this data and to have something in real time, it's almost, it's very difficult to implement. And basically, in this case, also there's this data is not enough. We don't have other kind of data that they may have, but they are not providing, in fact. So the idea is either you do collaborations specifically with relevant people in the Ministries of Health or to WHO in this case, or if not, it's very, very difficult. Yeah.
Okay. Thanks, Carlos. I suggest that we move on to the presentation by Sylvie. Sylvie Joussaume will be talking about more infrastructure aspects of climate research, and she comes from LSCE-IPSL in Paris. So the floor is yours, Sylvie.
Okay, now I am here. Okay, thanks. So I would like to talk about linking climate modeling research infrastructure, so really an infrastructure for research, and how that can be linked or serve or be useful for climate services. I am a climate modeler, and I am coordinating the European infrastructure project, which is called Easiness, and I would like to start to explain a little bit this context and then develop the point. So to start with the infrastructure, what do I call infrastructure in for climate modeling? The project that we have is called Easiness, which is infrastructure for the European Network for System Modeling. This is the network that gathers the climate modeling community in Europe, mainly the global climate models, but it also encompasses some aspects of the regional climate models as well. We have had already 2 phases of this project, and we are in the second phase. What we consider as the infrastructure for climate modeling is composed of the models, the climate models themselves, as well as tools associated to use those models, to run those models, the access to the computers and the storage, and the data and metadata, which are largely distributed for a range of users. In the case of easiness, we are completely focusing on the international coordinated experiments, which are the ones that are coordinated by the World Climate Research Program, WCRP, which are reference simulations, which are extensively used in IPCC reports, which are used also, so basically for climate research, but which are also used for impact research, and which are also, and I will show some elements, used for climate more recently by climate services, or at least some aspects of it. So I would like to focus on two aspects in the following: the simulations themselves and how much those reference simulations can be important for services and what it can bring to services, and the data distribution aspects, so the database, the data infrastructure aspects. On the reference simulations, so typically starting from the global climate models, what we call CEMIP, the couple modeling intercomparison projects, which are coordinated at the international level. The last exercise was done, CEMIP 5 was done between 2007 and 2014, basically. And encompassed 27 modeling groups, 58 models, because the modeling groups often use one or two different versions of the models. And we had 7 groups in Europe among those 27 worldwide. Those experiments are important to evaluate the models, to better understand processes, but also to produce projections, so estimates of possible future climates. It represents an enormous amount of simulated years of experiments. And last time for this exercise, we shared 2 petabytes of data altogether from those 58 models. The previous exercise, which was about 6 years before, was only 36 terabytes, showing you that it is expanding. So typically, the kind of results that are produced are here showing the projections for a high scenario, like the one LCP 8.5, more or less a business as usual, or a low scenario with a high policy mitigation strategy, which is called 2.6, which shows typically the change of the climate between the end of the 21st century and the end of the 20th century. The idea is not here to discuss in details the results, but more to show what is the background and what are those simulations. Typically, in IPCC reports, you will produce the evolution with different scenarios, which are the ones I mentioned, the 8.5 or the 2.6 below, and you produce with a range of models, a range of projections for possible future. The fact that this is coordinated internationally allows to have estimates of the uncertainty associated with their scenarios, and uncertainties for each scenario associated with the different models, which is the shaded area representing the range of the different estimates. The fact to have also this multi-model approach done completely consistently allows to have the multi-model mean, which often behave better than just each individual model, so which gives a bit more robust estimates. And typically from those results in IPCC, you will have for each scenario what is the mean, multi-model mean, what is the likely range, the minimum and maximum, and for different periods. So typically this is the information which is produced by these kind of experiments. The other aspects which is related is model evaluation. And this is also another important aspect for climate services, since it is important to know which reliability can we have in those models. So here, to show just an example, we can see that kind of slides or graphic in IPCC report, where you look at the pattern correlations between models and observations, here for the period 1980-1999, for different variables, surface air temperature, long wave radiation, outgoing radiation, precipitation, or cloud radiative effect. The multi-model mean is typically the bar here with the dots, and you can see CEMIP 5 in blue with the range of the models, CEMIP 3, which was the previous exercise, in dark, and observations, of course, which are the one which is used is typically at 1, so the best correlation with observations is 1, but you can have for some variables some different estimates from different observational data sets, so you also have some uncertainty in observations, which is shown in green. So the idea, once again, is not to go in detail in this evaluation, but to show that thanks to this database, you have a lot of information on model evaluation with better trust in some variables like temperature, less in some other variables like precipitation, which is much more difficult to simulate. Also better in long wave rather than in short wave. The other aspect of the infrastructure is the database and standards. For the research has been developed a distributed database called Earth System Grid Federation, which allows, so the data are stored where the different groups are, and there is a system of cataloging or searching services which allows the users to access all the data from the different sites as if they were all gathered in the same place. This was adopted since the database was too large to be transferred to one unique site. And this was only possible since we had behind that an adoption of a lot of common standards and conventions, like for the structure and format of data, for the metadata, for the vocabulary, for the documentation of the models and experiments as well. So all this standardization enables automation of the preparation of model output, analysis by the different researchers, and sharing of the data across this infrastructure. So typically in EasyNet, we support the European contribution to this System Grid Federation database. So what is linked with the climate services? I use here a diagram that has been prepared for European Research and Innovation Roadmap for climate services, which tried to show the overall chain associated with climate services. So typically, for climate services, we need aspects related with climate science. There is a need to have intermediate or translators interface like consultancy services, and you have all the users community. So this diagram tries to show how we go from the climate science to the end users. And this requires to have access to observations, to models, computers, to be able to simulate models, but also analyze observations and models. So model simulations, so typically the experiments I was showing, CEMIP experiments I was showing are here. From this you can provide climate knowledge. You may use directly that information at global scale, or need some regional downscaling, or need to run impact models using global or regional downscale products to provide this information. So what I showed is typically the climate research infrastructure is on this side and the climate services on the other side. So I tried to address the questions that have been asked by the Climateurope. So on which challenges are raised for climate modeling research infrastructure by climate services, looking at those two aspects, the data and metadata on one side, the semi-preference simulations on the other side. Starting for the reference simulations, typically we already have, thanks to those international coordinated experiments which are done for research, but it allows to provide multi-model, multi-scenario, and ensemble simulations, which are relatively well evaluated, so with a solid evaluation base. For climate services, what we see is that we need these, and this is a strong asset for climate services, but climate services may need larger range of scenarios, more extensive, often more ensembles, larger set of global regional projections, so typically be sure to have more consistent information, and often bias-corrected information, because there are some biases in the model output, so to be able to correct them, to be able to use more directly this information for different direct applications, and guidance how to use that. But we clearly see that we already have a strong existing base, but there are a need for some additions. The fact that there are those additions required for climate services is also something which is important for research, since it also offers to research a better quantification of uncertainties and allows to have a larger range of users which can feed back on the information provided by climate models. On the data and metadata side, we already have common standards for data and metadata. We already have a system of quality control, which is always improving, but which is already a certain level existing. But we see that for climate services, this is a strong asset. We can start from that, but there is a need to have a sustained, reliable service, so no break. And this is important for both research and service, but even more higher required for service. There are need for tools to facilitate usage. There are need for computing facilities for compute indicators. But the fact that we have this interlink between research and climate services can also add value for research, since it can provide an integration of models and observations, which is also something important for research. It can help to have consistent standards between the research part and the more operational part, like predictions, and it can help us support some further developments. Up to now, this link between research infrastructure and climate services is under development within the Copernicus Climate Change Service, C3S at ECMWF, where they develop a service for climate information with a climate data store, including reanalysis, satellite data, seasonal forecasts, but also projections, global and regional. There has been a precursor project, CLIPSI, and I will show another slide related to that. And there are calls up to now already ongoing with Copernicus, which indeed plan to broker on this database based on CEMIP and for the regional aspects on Cordex, called System Grid Federation. So for the global projections, it is already decided to broker on the SGF, and typically partners from INES, EasyNES community have answered to different projects, and there will be a node of the Copernicus brokering on the SGF. And for regional projections, there is an ongoing tender, but there is at least some answers that also propose to broker on the SGF. So we already have a precursor of those projects that can give an idea of how that can work between the research infrastructure and the climate service, which is this CLIPSI precursor project, which typically for the climate modeling, for the climate information from climate models, typically has relied on EasyNES and the international CEMIP experiments and the Earth System Grid Federation, but has also included in this portal access to observations and access to information from climate impact communities, so typically impact indicators. So this shows a first example of how we could more and more link in the future infrastructures for research to climate services. On the second question raised for the Climateurope for this webinar, how to manage the situation with the H2020 work program, where climate services show a tendency to be better funded than climate observations, model development, and infrastructure. It's clear that a diagram, that the one I showed previously, which is the European roadmap, it is quite key to recognize that to really have a good climate services, you need to have an overall chain. It is not just to support their translation level and the interface with the users. You need to bridge the gap between the research layer and the users. So this is one first aspect which, at least thanks to this typically this European roadmap, starts to be recognized. It doesn't mean that it is all, because there is still a need to support climate science if we want to have better understanding. So we need to show, and I think the meningococcus early warning system shows the need to have a better understanding. You cannot say that all is already known. There is still a need to improve understanding to prepare for future climate services. There is a need to improve the models, further improve them. Also a need to sustain the infrastructure if indeed we want to build other services on the research infrastructures. I tried to produce a SWOT analysis. This is certainly a work in progress, and this could most certainly still be discussed and improved on the research infrastructure and climate services. So showing the strengths and weaknesses of this research infrastructure and opportunities and threats associated with the fact that we have climate services which can be users of these research infrastructures. On the strengths, on the model simulation, the fact that we have those coordinated experiments, those reference simulation, is really a strong asset for climate services. It gives a better ensemble mean, it gives a range of uncertainty, well evaluated, a source of for downscaling, a facility to compute various indicators. On the data infrastructure, it gives a common database with common standards for data and metadata, and we clearly see that, for example, from the CLIPSI precursor project, we can use that for accessing and gathering information of different sources. So this is a strong asset for climate services. We have some weaknesses. On the models, we have a limited set of scenarios. Often they would like more scenarios. The models are better at large regional scale than really on the small scale. So there is a need for downscaling, bias corrections. So all this, of course, has some limitations. On the data infrastructure, this is distributed, which is good, but of course then is more difficult to be sure to be fully operational for services. It is, and more importantly, it is still project funded, so not really recognized as a long-term research infrastructure, which may jeopardize a long-term supported structure. It has opportunities. The fact that it can be used for climate services offers some opportunities to the community. It brings a strong added value. The fact that it will enhance the range of users. It will have a wider impact of those simulations. It can bring a better integration with observations and operational predictions, and this is also important for research. It may also provide some private funding by climate service users, although this may be a bit more difficult to set. There are some threats associated with that. The fact that we are not fully answering climate service needs may then push climate services to develop their own simulations. So we may weaken this link, and I think it will be not good both for the services and for the climate research. We may have, it may be a threat for climate service if we have difficulties to sustain the funding report for the research infrastructure. We may have some difficulty to support climate science because the climate services are more seen as key than really their basic science, but we still need the basic science. there might be, we have to make sure that the reliability of this infrastructure is sufficient for services. It may not be sufficient for services, so they may develop their own standards, their own ways. So we have to make sure that this does not occur. And the climate research infrastructure is an international structure with international governance, and this is independent of the climate services. So this governance, we have to make sure that indeed it can indeed continue and help serve the climate services. So here are the main messages I wanted to convey according to the different questions we have in this webinar. Thank you.
Thanks a lot, Sylvie. That was very interesting. I have to say that the last part is really useful in the context of Climateurope, as you already know very well. I'd like to offer the opportunity to any of the attendees to ask any questions. I have a question myself. Yeah. So just a question about one of the overheads that you showed about the IPC working group 1 report, in which you were talking about model evaluation without wanting to get into too much detail about this. One of the criticisms that the report has received, and that goes down to CINIP, is the slow progress in the model quality. Your figure shows that there's an improvement of the model reliability for the 4 variables that appeared in the figure. But is that something that should be included in the threats as well? The perception that the models are not improving quickly enough.
Yes, indeed. Yeah, it could be included in the threats. It's also related with the fact that the models are better at the large scale than at the smaller scales. So typically, with precipitations, there are more difficulties than for temperature, which is a bit more global scale than precipitation. Yes, that could be added. But that also calls for the second question when you ask the question on how to the risk to focus more on the services than on the climate science itself, is that indeed there are still a need to do progress, and there is still a need to further develop this science. I mean, we are in a research field, and things evolve with some time scale. And Carlos also mentioned that the time scale of research is longer than the time scale often required by the users would require much faster progress. But I guess we can use, I mean, it can be seen as negative or as a way also to trigger more research and still continue to advance on research. But the other aspects is that it's clear that we are also completely limited by the computers also, which is another aspect. So there is both the knowledge and the computing facilities which are behind these mislimitations as well.
Yes, I would like to highlight this again. This a little bit. I find a little bit of this misalignment between research and a more operational service. This is particularly challenging. As I said, some of the problems change over time, and for particularly maybe I'm talking more than in the generation of better climate data from models. Higher resolution, more detail, better skill. Also, this transition into services that the application itself in collaboration with the users. The problems tend to be, at least from my experience, and maybe I cannot generalize, but to be highly specific. And this high specificity demands really focusing on a certain problem for a certain amount of time. And particularly, I think I don't see an institutional or a kind of somebody that is occupying this part of the market. And somehow scientists that from different fields, we have to step into that and try to help doing that transition or that translation. That's necessarily not aligned with what you're supposed to be doing or your funding comes from, at least in the U.S. It is one of the problems that we had. So I would call also for this. I think that on the one side we have maybe to fund a little bit more basic science from the climate side, but also there's some, I would call it some basic science, but highly specific to specific problems that are important, and that there's no funding for that. So I think, as you said, finally to conclude, there's a chain. We don't have to forget about any element of the chain, and that the waves on how it's perceived by the funders now. I think there's a difference between the U.S. and Europe. The H2020 program is something that I don't see something similar in the U.S., for example. So it also depends where you are. You have a different perception of what's missing there.
Thanks, Carlos. Again, this is an opportunity for some of the attendees as well to raise express their opinions or raise any other issues. The other question that I have to both of you, to both Sylvie and Carlos, is what is your impression about measures that we could take that are not being taken now? So who are the actors that we have to link to that haven't been touched upon yet? And include everything here, and including IPC, the governments, what is, even if it's very ambitious, still to be done that we are not doing. Sylvie, do you want to start?
It's a difficult question. The actors, a lot of actors are touched by this question. It's probably more than a lot of their users are not yet. There is often a lack of awareness of the need of those climate services. So I guess the main issue is really to go from an interest to something where there is really a need and a stronger awareness. So we probably are still in this construction phase, which limits and which also requires that it is more funded by typically institutional or governmental level or European level, but not yet still from really the users. So I guess we are still in this phase where it is emerging. Does that answer your question?
Well, I don't know. I don't even know whether there is an answer to that question. It's more to know about your view about it. I was maybe thinking on what can be disrupted in all these situations that we have now. I know that this requires a lot of foreseeing and a lot of guessing about, and even science fiction of what could happen in the next 10 years. But what could we expect, or what could we pay more attention to that can change the things and speed up the process?
Well, I mean, probably it's a very constrained or limited point of view, but I feel that I would like to insist on the institutional alignment, and particularly we think on traditionally, for example, weather services. They have a specific mission, They have been providing service that is integrated in society. They are supported by the government. It's strategic. And this is a clear case that a service like for weather is working, right? When we talk about climate services, in my opinion, it's something that involves not only the data producer and having an infrastructure to produce that kind of data, which is also challenging in itself when we're talking about climate. We have to add the other side, how to link to the user. So in a way, I don't see globally or in any country any institution that tailors specifically in its mission very systematically in that sense, right? Also, climate services is very wide. The applications are very wide. Probably in some of the issues, private companies, of course, have to be involved and develop probably a business model when things are certain or certain products can be used. But there's an interface in which of the development of the climate service for it to be useful, and maybe also in some aspects there's not a clear business model to generate. So the companies are not going to be interested because they are not going to be interested on that because there's not a market for that. But somehow, who takes care of that in terms of developing this interface with the users? I don't see the institutional alignment happening. An example, for example, in terms of health, the miscommunication between WMO and WHO. These are completely different animals. It's very difficult to engage with users when already the experts are not engaging properly with each other. So, I think that before thinking about how we engage specific users, also we have to learn how to engage with different expertise that are needed to provide a service that is going to be used, that is relevant, a product that is going to, in the case of health, that is going to save lives, a product that is going to help farmers in their business, etc. Okay, thanks, Carlos. Sylvie,
on one element which may not be the whole story, but when you talk about disruptive, there has been a proposal from the climate modeling community that if we could speed up the development of global models at very high resolution, like the kilometer scale, with computing facilities accessible, associated and prepared, we could really have a much better climate information base, at least for things like extreme events. So that could be one disruptive type of information, and has been proposed as a flagship. It doesn't mean that it solves all, because we also need to have more embedded knowledge with and modeling with the impacts. I mean, there are a range of aspects which are needed, but clearly on the climate side, this flagship could be quite disruptive.
Okay, thank you. That's very interesting. I think we have to stop here because we've already been going on for more than 1 hour. I would like to thank the two speakers to be available, not just today, but even for during the preparation of their talks and the preparation of the testing of the sound and the video. So I really appreciate the discussions at the end. I think they will be very useful for the preparation of some of the Climateurope reports. And as usual, as you know, the presentations and the discussions have been recorded. They'll be made available on the Climateurope website, as the previous webinar has already been. So you can find the previous webinar as well in the Climateurope website. Before closing, just reminding that this is a series of webinars. Stay tuned if you want to take part or listen to the next webinar.
Thank you very much and have a nice day.
Thank you.
Thank you very much.
Bye.
Bye-bye.
Yeah.